Thanks to everyone today for having me. Yeah, as Juliana said, my name is Nico Vincent, working currently at ZF Friedrichshafen in the south of Germany in Friedrichshafen. Currently employed as part of the red team. Previously was part of the autonomous driving division at ZF, where I'm also was partly responsible for introducing fast testing into our cybersecurity process. And yeah, that's exactly also today's topic I want to talk about. So how can we integrate fast testing into an automotive cybersecurity test strategy? But before we dig into that, I'd like to establish just some context here. So let's have a very brief recap into the product development process and a cybersecurity test strategy. So basically, every product development process we have is accompanied with a cybersecurity engineering process where we start with a TARA, which is a risk-based approach for defining cybersecurity requirements. And based on those requirements, we derive cybersecurity features, which go into our product design. We implement them, integrate them, have a cybersecurity verification validation, and then start production. So far, so good. The cybersecurity test strategy we usually have should include at least those things as functional testing, where we take a look if functionally our cybersecurity specifications are implemented into the project. We do vulnerability scanning, where we say, okay, we have a software bill of materials of our product. Let's look if based on known vulnerability databases, if any vulnerabilities which are known within our product. And we do penetration testing, where we take some human experts, which take manually a look into the product and see if they can exploit anything. And of course, what we want to do now is accomplish this with a fast testing process. So, and how can we do that? I have a very quick rundown how fast testing can be integrated in a cybersecurity test strategy, which is basically first thinking about which kind of activities we need within our development process regarding fuzzing, then defining work products which are necessary for it. Creating a fast test specification, which is tailored for our product, the report, which is the output of it, then having fast testing as a continuous activity, and finally thinking about which kind of other cybersecurity engineering process CP activities are interfaced by our fast testing efforts. So starting with fast testing activities within the development process. Maybe one of the most important takeaways from today is that fast testing is nothing you can just do at the end of your development phase and are done with it. So, for example, we see here the A-Space V model, which is commonly used for development. So it's not just that you would build your product and then after you're done with it, you start testing, but it's really that you continuously from the beginning need to apply fast testing. So even at your software unit stage, you need to do it. And it's also not some kind of a monolith activity, but it's really a split between software and system level fast testing, because as we later see, we have just different needs and just a different structure when we look into the software and the system level. And yeah, for having a process, of course, we need also work products for it. One is the base for it, which is our fast test specification, where we clarify, okay, what do we want to accomplish with our fast testing and how are we going to accomplish it? And of course, the fast test report, which gives us a list of findings, but it's not limited to that, which is also a very important factor of it, is that we have evidence that a sound fast test specification was created by us as well with this report. And yeah, starting with our first work product, the fuzz test specification. Basically, we have two leading factors for our test specification, which is the fuzz test scope and our fuzz test methodology. Both is determined by assigning a test rigor level to assets of our fuzz test target. And yeah, cybersecurity assurance levels are a helpful tool for doing that. As you can see here plotted, call 0, which will be basically the least rigor, the least assurance we need, until call 4, which is like for highly critical rigor, meaning that we need more test rigor there for assets or interface assigned to that. And of course, an intuitive point of time for doing or assigning those calls, those levels, is during the creation of the Tara, where we have to look into all the interfaces and assets anyway. In an ideal world, of course, we could test everything with highest rigor, which means yeah, we would just assign call 4 to everything and test forever and test it really well. But of course, in the real world, it's not possible because we have limited resources, limited time, cannot test forever. So we have to need some way to yeah, to tailor away things which are not relevant and prioritize our test efforts. And the Tara gives us guidance there, which parts are out of scope. Regarding the fuzz test methodology, yeah, we should, within the specification, already decide which kind of methodology we want to apply to our product and its different cybersecurity assurance levels. And there are multiple characteristics which decide which kind of rigor our fuzz test has, which is basically the test level we have, the system under test setup, our program structure awareness, the fuzz test input, and the kind of instrumentation we use. And then we have as output yeah, metrics about code coverage, test cases, time, and of course the findings we get from it. Test level, we just saw it earlier. We have different test level on software and system level fuzzing, and with different test levels, of course, we have different kinds of tests we do. So on the software level, of course, we only have source code available. So we can already start really fuzzing single functions, code units or attaching to a program API, whereas on the system level, we would really have already a completely integrated system, which provides us with system interfaces, which we could fuzz, such as, for example, CAN, FlexRay, Ethernet, or also some files which we could supply, such as config files or certificates. Regarding our system under test setup, it's really important which kind of setup we provide for the test. So the initial state and also the transitions we have are play a big role how well the test goes. So for example, some kind of products would need some REST simulation to even start up correctly and have a correct initial state without going immediately into an error state. And also for some kind of state transitions, this is necessary. Furthermore, we would, for some kind, also need some credentials. So for example, like a secure access state or something like that, where the fuzzing tool could never reach it without having that credentials provided. The program structure awareness plays a big role. So the simplest thing we could have is, of course, a black box fuzzing tool, which doesn't know what's going on our test target. I mean, the good thing about that, or the advantage, is that it's very easy to set up. Disadvantage is, we don't really know what's going on. Opposite of that is would be white box, where we really have all our code available and could bulkily analyze it by a white box fuzzing tool. Has the downside that it's very it's very time consuming and hard to do, often because we have dependencies which we cannot resolve. So we have a middle ground, which would be a gray box approach, where we use instrumentation, which attaches or is linked to source code, or the system which allows us then to trace where our code is executed. We have also different kind of test rigor for the fast test input. There are two approaches. One is having generation-based input, where we would, in the least rigor, just supply some pseudo-random generated input, having a downside that it wouldn't penetrate very far into the system. So if we want to have more test rigor, deeper penetration into the system, we would need some kind of formal grammar or model describing the interface very well. And having at specific points defects or some malicious changes implemented, which will then penetrate or may cause some defects into the test target. The same thing with mutation-based input, where we will have a test corpus, which is built based on valid input data, which is then on certain fields mutated for causing those defects. And finally, I mentioned earlier the instrumentation. There's also different kinds of rigor we have for the applied instrumentation. So the most straightforward one and easiest one to do is just have inbound instrumentation with my test target and look into the answers it provides us, the response messages. The easiest one is just looking if it's alive. A bit more sophisticated would be if we look or try to analyze the kind of message we get there. Regarding external instrumentation, that would be a better kind of or more sophisticated approach, where we really have either a debugger attached already to the test target, or have some kind of agents linked into it, which can exactly tell us what's going on during the test. Yeah, and after we have our methodology going, the fast test done, of course, we get some results back, which we should process into a report. And there's basically following things we get is the code coverage, test case, and time we spent as metrics, which tells of course something about the fast test quality, but they are only conclusive when they are linked to to the test specification. So of course I can see that if I have maybe 30 days of test time and 0% of code coverage, then there's some issue, but I really need the test specification to understand what exactly the metrics mean. Regarding our findings, the most important thing I want to stress here, and that's also the reason I put it at the first place, is that it really should, in the process, it should be clarified who is taking care of the findings, such that we're just not doing testing and nobody ever implements those fixes for the issues we find. The findings itself, they provide, they are as findings conclusive, but they do not provide lots of evidence regarding, like, if I had really good fast tests. So if I, for example, don't have any findings, I cannot conclude that I'm done with fast testing or that my fast test was good. But it's really just conclusive if I also know the test specification and which kind of test was done there, with which kind of methodology, and whether it was appropriate for the test scenario. After having established those work products, of course, we want to not do it the tedious task of doing it manually every time, but we want to have it continuously within our process. So we should have a continuous activity here. I just want to sketch one kind of CI workflow, which would be possible to do here. Of course, this is very dependent on which kind of process you decide on the end and what kind of setup you have at your company, or which kind of tooling you have. The workflow I sketch here would be for a software level fast test. So a developer, for example, could just write fast tests for some kind of software, push it to a version control system repository, the fast test branch, which will trigger a pipeline build on an automation server like Jenkins. You would then have it automatically deployed on your test system. The fast test would be triggered. A fast test server would run those tests, get the feedback, and the result would be reported back to the automation server. And finally, either leading to the pipeline succeeding or failing. And if there were issues found, those should, of course, automatically be tracked in an issue tracking server, where then the developer gets those issues reported so that he can start an investigation what went wrong. And after having all those findings, of course, we want to see how other cybersecurity engineering process activities can now benefit from having such a process established. And taking a look back to our now more complete test strategy, we have following things we can do. We have, of course, based on the fast test report, the findings we have use for functional tests to generate negative functional test cases. We can vulnerabilities we might find directly import in our vulnerability database we have, and we can use, if we found some kind of sketchy behavior or some kind of undefined behavior during the test, we can use this for as basis for further investigations during a penetration test. The fast test itself can be used also for refining the tower. So if maybe we find that the modeling of the tower or some kind of methodology or some kind of rigor or cybersecurity assurance levels we defined were not correct, and we can refine the tower from that and directly use the new findings to refine our test specification with it. So in summary, the points I would like to stress the most is that it's really important to establish a fast test process before the project, such that when a project begins for developing a new product, we can really start activities early and continuously throughout the whole project. The test specification is really important for having a sound fast test, so it's really important to take much time for working on that. Responsibilities should be clarified early and for all objectives, and activities should be wherever possible automated, because it's tedious to do them manually. And following all those things, vulnerabilities will just be found earlier during the process, during the tests, and during the whole development, and this causes our remediation costs to be lower in the end. And this is already the end of my presentation, so thank you very much for your attention. And if there are any questions, I'm more than happy to answer them. Thank you.
Looks like I was on mute for the last few seconds there. Thanks, Nico. Sorry about that. So thank you so much, everyone, for joining the CI Rewind on integrating fuzzing into automotive cybersecurity test strategy. And thank you to Nico for joining us for this live Q&A. If anyone has any questions yeah, please post them in the chat and we'll be able to see them and answer them for you.
Oh, hi, everybody. Happy to answer some questions.
All right. It looks like we've got one. So let me just put that on the screen. Would there be any challenges in going between fuzz testing and pen testing?
Going between. Okay, I'm not entirely sure what this question means. Maybe I try to interpret it. So what we have is, of course, fuzz testing is one part of penetration testing. It's usually a subset. So of course, the findings I have from fuzz testing largely benefit than doing my penetration testing. Yeah. If there is maybe more specific info you would like to have, please, maybe you can conclude on that question.
All right. All right, looks like we've got another question here. So yeah, could you summarize the big idea of what goes into this rigor decision-making process?
So the big idea is, yeah, as I said in the presentation, the rigors really depend on the methodology you have. So really thinking about okay, which kind of rigor do I need? Yeah, based on my findings from the Tara, and then okay, how can I put this rigor into my methodology? And then of course there's no black and white, but if you say okay, I have something like Cal4 with maximum rigor, then I of course need a very sophisticated methodology. Whereas when I have very low rigor, I maybe can get away with only doing some simpler tests on it, and doing less testing time.
Okay. We got one question here. What challenges do you typically encounter when performing system-level fuzzing? I'm thinking of ECU, internal states, etc.
Yeah, exactly. So the biggest challenge doing fuzzing on system level is of course your feedback channel. Doing it on code level, it's much easier to compile your address sanitizers in there, etc. Doing it on system level, you usually only have the interfaces, so you can do inbound instrumentation, which does not tell you about okay what's really going on in your memory, which kind of address leaks or issues you might have, memory leaks and overflows you have. So really getting agents in there compiled into the system is quite challenging on your system level. But it's nevertheless doable. It just takes, of course, a lot more effort to do.
Looks like we've got one more question here. I see. Just put that up. So when taking care of the findings, is this only something that can be done at the end when considering the reports, or can it also be managed continuously?
Yeah, I mean, it must be managed continuously. So you really should, when you have this integrate into your CI, of course, having pipeline failures when there are findings, and then you have to take care of them all the time, because if you are not going to do that and do everything in the end, then you have so many findings and are no way able to fix them all in time. Yeah. So it's a continuous task.
All right. Just give it another minute to see if anyone has any more questions. All right. Thank you so much, Nico, for your time. And thank you everyone for joining. If you would like to see Nico's talk again or any of the other FuzzCon Automotive talks, you can just check them out at fuzzcon.eu/automotive-edition. I can put that up on the screen here for you. Yeah, and thank you everyone for joining, and have a nice day.
Oh, thank you for having me, and thanks for the questions. Have a nice day. Goodbye.
You too. Take care. Bye.